This is an electronic components training stand. The stand is mounted on a base frame. It can be used in multiple configurations. It can stand upright, as it is now, or it can be rotated, its legs folded and laid flat on a table in a horizontal position, depending on what's most convenient for students. It can easily be used on a table or as a freestanding unit. This training stand is equipped with a wide variety of electronic components. There is a group of resistors, divided into sections. Next is a resistor decade box, also known as a resistance decade. There are several potentiometers of various sizes, and a group of capacitors with different capacitance values. Inductance coils are also included, with different inductance ratings. Various types of diodes are present, including both LEDs and photodiodes. Additionally, there are several groups of transistors. Here's an NPN-type transistor, as well as N-channel and P-channel. The stand includes thermistors, NTC type, with different values. An audible signal is also installed. Two different types of switches are available. A DC motor is included. There's also a 5-pin automotive relay. Several different types of bulbs are available, including single-contact incandescent bulbs and 2-pin incandescent bulbs. There is an LED bulb, as well as a dual-contact LED bulb. We also have a phototransistor. Power supply terminals are included, with both positive and negative connections. The stand includes a pulse width modulation PWM generator. There is also a power supply voltage regulator. A few fuses are installed, and a multimeter is included as well. You will also find a set of connecting wires, neatly arranged on the side. These wires are intended for connecting various electrical circuits and components, and can also be used with the multimeter for measurement tasks. They're suitable for all basic measurements. The stand is powered by a standard household electrical network. When connected to the mains, the stand is powered on. A power source and supply unit are activated, and all necessary switches are enabled. The voltage at various measurement points or terminals can be adjusted by using the voltage regulator knob. By rotating it, we set the required voltage level. The output can be fine-tuned as needed. By turning the potentiometer here, we can increase or decrease the voltage. At this moment, the output is 12.2 volts. If we adjust it downwards, the voltage can be reduced to 3 or 4 volts, depending on what's needed for the task. It's fully adjustable to suit the work. The stand includes a standard set of 6 power cables. If more wires are needed, we can easily double the amount. These extra wires are kept in storage and can be provided as required. Every component on this board has its parameters detailed in the manual. You'll find the specifications for each part. These include the technical characteristics such as resistance values for resistors, operating temperature ranges, power limits, maximum current, and more. All of this is described in the technical documentation. The stand is designed so that all the components can be visually identified from the outside. Resistors, capacitors, coils, diodes, transistors, and bulbs are all visible and easy to access. Only a few exceptions are hidden internally. The resistor decade box, for example, is built inside. Same with the potentiometer. These are mounted inside the panel. That's a small detail, but important. You'll often see the symbol of a component in the circuit diagram. Then you can match that to the actual part on the stand. So you can easily identify both the schematic symbol and the physical component on the training stand. If needed during measurement tasks, you can detach the multimeter from the stand and place it anywhere convenient for comfortable measurements. It's fully portable and adaptable. The multimeter is removable and can be transported easily to wherever students need it. If it's not in use, there's a practical solution. The multimeter is equipped with double-sided adhesive tape, so it can be fixed securely in its designated position. Now let's look at a few practical demonstrations to understand how to use the stand. We'll connect a few basic circuits as examples based on simple diagrams. These are very basic, easy setups, just to demonstrate functionality. Let's begin with a simple LED connection. We'll connect an LED. Since it's a light-emitting diode, it should be used with a 12-volt power source. To power the LED correctly, we must connect it through a 1 kilo ohm resistor. We connect the positive terminal to the LED, and the other terminal of the LED is connected to ground, minus. The LED lights up. If we had connected it without the resistor, the LED would have burned out instantly. In such a case, we'd need to open the stand and replace the LED. Always make sure to include a resistor in the circuit. Now, let's build another simple circuit, this time using a frequency generator. We'll try to control a light bulb with a pulse width modulation PWM signal. As we adjust the signal, we'll observe how the bulb's brightness changes based on the duty cycle and frequency. Let's start by connecting power to the bulb. We begin the wiring. We connect the negative terminal to the PWM controller block. This controller regulates the negative ground side. It doesn't supply a positive signal, only controls the minus. The positive is fed directly to the consumer, the bulb, and the ground is controlled like a switch placed after the load. This switch turns the circuit on and off. Although everything is connected correctly, the bulb hasn't turned on yet because the voltage regulator still needs to be powered on with its own switch. Currently, the stand is off, so we need to press the button to activate the regulator. Once pressed, the voltage regulator starts working and supplies power to both the PWM block and its connected terminals. In this case, the bulb begins blinking. It flashes at a steady frequency. Currently, the frequency is 1 Hz, which means the bulb blinks once per second. At a 50% duty cycle, the bulb is off for half a second and on for the other half. This is the definition of a 1 Hz signal. Let's now increase the frequency to 20 Hz. 20 Hz means the bulb will blink 20 times per second. That's 20 cycles. So in 1 second, it turns on and off 20 times. And that continues constantly. We'll now reduce the frequency back down to 1 Hz. Let's now change the duty cycle to 20%. This means the bulb is only lit for 1/5 of each second, only briefly. The bulb is off for most of the time, and on for a very short duration. Now, let's adjust the duty cycle to 80%. This flips the ratio. Now the bulb is on for 4/5 of the second, and off for just 1/5. The change is clearly visible. The bulb glows much longer than before, only briefly turning off. You can see a major difference now. Previously, it was off longer than on. But now the opposite is true. It stays on longer than off. Let's now demonstrate how frequency affects brightness. Again, we use a 50% duty cycle. At a 50% duty cycle, the bulb turns on and off evenly. Right now it blinks once per second. Let's now significantly increase the frequency. At 330 Hz, the bulb appears to be steadily lit. There's no visible blinking anymore, but its brightness is noticeably reduced. Now let's reduce the duty cycle. We'll bring it down to 20%. The bulb remains lit, but very dimly, and there's still no visible flickering. It glows faintly, because earlier we saw that the brightness depends heavily on how much time the current flows. Let's now increase the duty cycle to 80%. You can see it getting brighter. At 100% duty cycle, the bulb reaches maximum brightness. It behaves like it's constantly powered. Now let's connect another circuit. This time, we'll use a multimeter to measure current. First, connect the COM port to this terminal. Then, from the bulb to the potentiometer. Now we power on the multimeter. We switch to current measurement mode. At this moment, the potentiometer is turned to its maximum setting. We're measuring a certain current level, and the bulb is glowing brightly. Now I'll rotate the potentiometer downward. As I reduce the resistance, the light dims. You can clearly see the current reading on the multimeter and how it decreases in real time. As the current drops, the bulb gradually dims until it stops glowing completely at a certain low current value. That point marks the minimum threshold for illumination. If we increase the resistance again, the current rises. The bulb begins to glow again, eventually reaching full brightness. Now let's test the sound signal device. We'll turn it on, powering the circuit. We'll control the buzzer using the same PWM device. Let's connect it. We begin with a 50% duty cycle at 1 Hz frequency. Increasing the frequency also changes the sound tone. In this case, we'll demonstrate resistance change using a 10 kilo thermistor. We observe its initial resistance value. You can heat it with a hot air gun or just with your hand. As the thermistor warms up, its resistance changes. Being an NTC type, its resistance decreases with rising temperature. So, as it warms up, the resistance gradually drops. When I remove my fingers and it cools down, the resistance starts to increase again. Now let's connect a circuit with an automotive relay to see how it can be used in control applications. We'll use a basic switch. The system includes a power source. We wire the relay coil from the switch terminal. Let's proceed with the next wiring. We can connect to terminal 30 here, for example. If we know this is a constant positive voltage, we can wire it like this. No problem. Either way works the same. The only difference is that in this configuration, the wire carries a higher voltage and current. Now let's control the circuit from this side. We'll connect an electric motor. One of its contacts connects here. Let's connect it up. Go ahead and attach. Also, a bulb. The full circuit is now wired. When we flip the switch, the relay activates, the bulb switches off, and the electric motor turns on.